In early 1948, a Soviet design bureau began developing a new fighter, the I-215. Swapping out the engines was far from easy, but that was just the beginning. Using flight data from the older I-211, the engineering team introduced several major design upgrades. For instance, the rudder proved to be too sensitive, requiring a significant reduction in surface area. They trimmed the bottom section and replaced the gap with a fixed tail fairing that blended smoothly into the fuselage. The elevator was fitted with an electric trim tab, which was a fairly advanced feature for the time. On the I-215, the ailerons were now driven by rigid metal pushrods instead of traditional control cables. This was a crucial upgrade, as cables had a tendency to go slack during wing flex in flight. Designers also reinforced the landing gear doors, the weapons bay hatch, the nose section, and the blast tubes around the guns. The armament got a complete overhaul as well, with the new fighter being armed with powerful 120 PM cannons. Standard ammunition capacity was bumped to 35 rounds per gun, though the magazines could physically hold up to 40. Inside the cockpit, they installed a new AP-1M gun sight. Its best feature was that it could be slid out of the way during landing, clearing the pilot forward view of the runway. Integrating the British Rolls-Royce Derwent engines promised significant advantages. Each engine produced over 3,300 pounds of thrust, weighed significantly less than the original Soviet TR-1 turbojets, and boasted a much longer service life. This engine swap alone shaved over 1,100 pounds off the aircraft weight. For comparison, the older I-211 had a maximum takeoff weight of over 16,400 pounds, while the new I-215 came in at just under 15,200 pounds. However, integrating these new power plants required massive structural modifications. Engineers had to completely redesign the engine controls and fuel delivery systems from scratch. The starting system was also overhauled. The TR-1 relied on a turbo starter, but the new Derwents required an external power cart for startup. But the toughest challenge turned out to be designing the new engine mounts. The TR-1 used an axial flow compressor. As a result, its center of gravity and primary mounting points were located near the middle of the engine casing. The Derwent 5, however, relied on a centrifugal compressor, which shifted the center of gravity much further forward. To fit this new setup within the aerodynamic profile of the wing, the team built an unconventional trough-shaped engine mount that projected well ahead of the wing leading edge. The engines rested on this frame via their side mounts, and an additional support point was added to the center of the structure for extra stability. By early April, the transition from the I-211 to the new I-215 was complete. The finished fighter was rolled out to the airfield. Following thorough ground checks, official factory trials kicked off on April 18th. Veteran test pilot Alexei Popov took the controls, while lead engineer Vladimir Molokhaev managed the testing program. First up on the agenda was calibrating the standard airspeed indicator using a specialized flight data recorder called a barospeedograph. It might sound like a routine procedure, but the team took it very seriously. They brought in 2 teams of specialists operating cinetheodolites, which are specialized cameras used to precisely track an aircraft flight path. They even sent up a specially equipped Po-2 reference aircraft to assist with the calibration. On the ground, tracking cameras were set up roughly 1.2 miles apart. To ensure the ground footage and the onboard instrument data synced up perfectly, second by second, all the equipment was linked using radio synchronizers. The pilot, Popov, would climb to roughly 3,300 feet. He would then make high-speed passes right over the airfield. In the cockpit, his indicated airspeed fluctuated between 215 and roughly 440 knots. Meanwhile, the ground cameras simultaneously calculated his true ground speed. At the exact same time, a PO2 support plane flying at that same altitude collected weather data such as atmospheric pressure, temperature, and wind speed. These grueling test flights continued all the way until June 20th. The team also flew 3 separate sorties specifically to establish the climb rate of the new fighter. The test profile required the aircraft to accelerate to an entry speed of around 300 knots. It would then pitch up into a steep climb. For every 3,000 feet of altitude gain, the pilot intentionally bled off about 8 knots of airspeed. They achieved their best results with an entry speed of roughly 310 knots. the I-215 hit the 16,000-foot mark in 2 minutes and 57 seconds. However, that was 21 seconds slower than the engineers had projected on paper. They attributed this lag to the engine intakes being too narrow, which starved the engines of airflow. This was compounded by the fact that the aircraft weighed over 400 pounds heavier than originally designed. Top speed tests, on the other hand, were much more successful. The actual flight data almost perfectly mirrored the initial theoretical calculations. Speed was measured with the engines running at a steady 14,700 RPM, and each high-speed test run lasted exactly 5 minutes. Down on the deck, the I-215 could hit 520 knots. But as altitude increased, performance gradually dropped off. By the time it reached 16,000 feet, top speed had fallen to around 500 knots. To get precise data on takeoff and landing characteristics, the specialists brought in trajectory tracking cameras and stationed ground observers at both ends of the runway. The flight data revealed just how tight the margins were. Test pilot Alexei Popov had good reason to be nervous before his maiden flight. The factory runway was barely long enough for a textbook landing under perfect conditions. The takeoff and landing rolls of the aircraft ranged around 3,000 feet. If even the slightest issue or deviation occurred during touchdown, the fighter would simply run out of runway. The test team was especially interested in evaluating a piece of cutting-edge technology for the era, aerodynamic speed brakes. They deployed almost perpendicular to the airstream at an 80-degree angle. Tested both in smooth, level flight and during steep dives, they proved highly effective, demonstrating that air brakes were an absolute necessity for jet aircraft. The maximum allowable deployment speed was roughly 460 knots. In a steep dive at 440 knots, deploying the air brakes for just 10 seconds rapidly bled the speed down to 300 knots. In level flight at 345 knots, hitting the brakes bled the airspeed off and pegged it right around 265 knots. Deploying the speed brakes did cause a slight pitch-up tendency, but the pilot could easily trim the fighter out without any extra effort. On June 23rd and 24th, the jet was sent to the factory firing range for weapons testing. Over those 2 days, they ran an extensive series of live fire tests, expending 572 rounds of ammunition. The armorers zeroed the cannons during live fire at a standard distance of roughly 160 feet. They also tested firing all the cannons at once, running through everything from single shots to heavy bursts of up to 35 rounds. The mechanisms worked flawlessly. During the tests, there was not a single defect, jam, or weapon failure. Of course, that did not mean the other critical systems of the aircraft were problem-free. Over 2 months of intense testing, the team had to tackle a number of complex technical challenges. For example, during the initial test flights, they discovered a major issue. Aerodynamic forces were literally sucking the landing gear doors open in midair. To fix this, they installed hydraulic locks on the front of the nose gear doors, added hydraulic actuators and extra latches in the middle, and fitted upgraded locks on the main gear doors. On top of that, there were serious ergonomic issues. The control lever for the speed brakes was originally located on the left side console, slightly behind the pilot. Reaching back for it was incredibly difficult and outright dangerous, especially while pulling G-forces in a dive. So they ditched the lever and installed a standard electrical toggle switch on the front panel. The engineers decided to defer fixing some of the more complicated defects, as these fixes would have required completely tearing down the airframe. Specifically, the plumbing between the fuel tanks was poorly designed, and the check valves of the fuel system were highly unreliable. But fixing those issues would have meant pulling out all the fuel tanks to upgrade them. Even though many historical sources mention that the I-215 was flown by several test pilots, the official factory reports only retained the flight test notes from one Alexei Popov. He gave the new interceptor very high marks. According to his reports, the cockpit was surprisingly roomy and comfortable. The instruments and controls for the engine, stabilizer, flaps, landing gear, and brakes were laid out perfectly. Popov noted that during ground taxi, the aircraft tracked straight and true, and the brakes were completely reliable. Liftoff was very smooth, though the aircraft did have a slight nose-up pitching moment during the climb. In level flight, even at top speed, or during steep turns and glides, the I-215 was incredibly stable. The pilot could fly hands-off and the fighter would track straight and level. If the pilot pulled too hard on the stick, the aircraft provided a clear warning with a slight airframe buffet. The stick forces remained relatively light, and any residual pressure could be easily trimmed out. About the only real downside was the heavy roll control. At medium speeds, the aileron stick force was around 22 pounds of force, but at top speed, that pressure actually dropped to a very comfortable 9 to 11 pounds of force. By mid-August 1948, chief designer Semyon Alexeyev officially signed off on the successful factory trials of the I-215. The team believed they had created a capable and reliable aircraft suited for mass production. However, the political and technological landscape had shifted. The Soviet leadership already had access to aircraft designs with far superior performance, and the new benchmark was breaking the 600-knot barrier. While the paperwork for the I-215 was still being signed, more advanced swept wing fighters, such as the MiG-15 and La-15, were already undergoing state trials. As a result, the Soviet government ordered a consolidation of the aviation industry, shutting down several organizations. Despite the work completed, Alexeyev Design Bureau was closed, and work on the I-215 was halted. Still, Alexeyev remained a highly valued specialist. By October 1948, he was appointed chief designer at a highly classified facility. Hidden behind a secret code name, this experimental plant housed deported German aircraft engineers. These foreign specialists were split into two separate design bureaus, one focused on jet-powered aircraft and the other on rocket-powered designs. The plant was established in present-day Dubna, taking over older aviation facilities. The facility director at the time was Viktor Abramov. The backbone of that first design bureau was made up of former staff from the aviation department of the joint Soviet-German enterprise in Dessau. The team was led by a talented German engineer named Brunolf Baade, with Soviet specialist Pyotr Obrubov appointed as his deputy. The core design team also included some heavyweights of German aviation, such as Hans Wacke, the man behind the Ju-287 jet bomber project, and Johann Hasselhoff, former chief engineer of the Junkers plant. Advanced aerodynamic calculations were led by Dr. Gerhard Backhaus, the former head of aerodynamics at Junkers. Semyon Alexeyev's time at the experimental aircraft plant was relatively short. In the first half of 1950, he transitioned to the Flight Research Institute to lead the development of flying testbeds. But even in that brief window, he accomplished some highly significant work. When Alexeyev first arrived, the team was already hard at work on two major projects. The first was Aircraft 140. The Germans called it the EF-140, a twin-engine bomber featuring a forward-swept wing. The plan was to equip it with the Soviet AMTKRD-01 turbojet engine, designed by Alexander Mikulin. Brunolf Baade personally led the second line of development. This was another twin-engine jet bomber featuring a conventional swept wing, later redesignated as Aircraft 150. The designers intended for this bomber to hit speeds around 540 knots with a maximum takeoff weight of over 66,000 pounds and a bomb load of roughly 13,000 pounds. The engineers incorporated several highly advanced design features for the era. The engines were podded under the wings on pylons. It featured a new hydromechanical flight control system, single-piece wing panels with internal corrugation, a T-tail, and a unique explosively triggered fire suppression system. One of the most interesting features of Aircraft 150 was its bicycle landing gear. This unconventional configuration significantly reduced the overall weight. On top of that, Baade wanted the bomber to squat on its rear main gear during the takeoff run. This artificially increased the angle of attack, making rotation much easier and drastically shortening the takeoff roll. The advantages were obvious, but the engineers ran into a major issue. At the time, aircraft typically steered on the ground using differential braking on the main gear. But on Aircraft 150, this setup was completely impractical. The main gear track was too narrow relative to the center of gravity, and adding brakes to the small wingtip outriggers just was not feasible. This meant the design team had to invent an entirely new nose-wheel steering system from scratch. They needed mechanical control logic to adjust the nose gear steering angle based on taxi speed, as well as during the takeoff and landing rolls. To perfect the new steering system, they built a full-scale ground test rig and used a German Junkers Ju-388 as a flying testbed for specific components. However, building a ground rig to accurately simulate the nosewheel steering dynamics proved almost impossible. It became clear they needed another flying testbed. The idea to use the I-215 fighter for this purpose likely came directly from Alexeyev. The German specialists had heavy restrictions on their movement and could not travel freely, making it highly unlikely they even knew the fighter existed. Historical sources often claim that a backup prototype designated I-215D served as this flying testbed, supposedly purpose-built with bicycle landing gear. However, the facts just do not add up. Archival documents directly debunk the existence of an I-215D model. The official test report for aircraft 155 clearly states that it was actually Alexeyev-1 and only I-215 prototype, simply retrofitted with the modified landing gear. Soviet state security was highly unlikely to let the interned German specialists leave their restricted camp. Having them show up at another aviation facility would have raised too many red flags. Most likely, all the modifications were done right there on site at the experimental plant. The revamped aircraft was designated as Aircraft 155. For the flight tests, the engineers basically just needed a flying testbed to evaluate the new landing gear dynamics, so they tackled the job as practically as possible. They immediately ditched the idea of making the landing gear retractable. The placement of the gear struts was dictated by the strict requirements for Aircraft 150, which dictated that 40% of the weight rest on the forward strut and 60% on the rear. To hit that perfect balance, they shifted the nose gear slightly aft and bolted it rigidly to the hardpoints that used to hold the cannon mounts. The cannons themselves were completely removed. The ideal spot for the rear strut ended up being exactly where the rear fuel tank was located. By removing the tank, the engineers did not have to make any major structural modifications to the airframe. They simply passed the landing gear strut right through the access panel opening. Both struts were fitted with dual pneumatic brakes. Brake pressure was applied to all the wheels evenly, but they used a special steering control valve that slightly delayed the air pressure to the front wheels during braking. Conversely, when the pilot released the brakes, the pressure release was delayed on the rear wheels instead. This clever bit of engineering safely kept the aircraft from nosing over during hard stops. Since aerodynamic efficiency was not a priority for this flying testbed, the landing gear setup was an absolute aerodynamic nightmare. The forward gear featured a massive steering mechanism wrapped in a tangle of hydraulic lines, while the rear gear looked like a crude truss welded together from heavy steel tubing. Despite this, the front wheels could still deflect 20 degrees in either direction. To keep the aircraft from tipping over, outrigger struts were installed under the engine nacelles. These struts were fixed and did not retract during flight. Their wheels were fully castering and equipped with centering springs to prevent them from shimmying in the slipstream at high speeds. The primary focus of the test program was ground handling. Test pilots evaluated how the aircraft handled during a takeoff roll without using the brakes and during the landing rollout with heavy braking. They tested ground maneuvering at speeds up to 20 knots, landed with lateral drift to handle crosswinds, and tested the gear on snowy, wet, and completely iced-over runways. Official testing kicked off in June 1950 with former Messerschmitt pilot Ludwig Hoffmann at the controls. Initially, the front gear steering mechanism was designed to adjust its sensitivity based on airspeed, but the very first taxi tests were a massive disappointment. The steering system proved to be highly ineffective and cumbersome. The engineers quickly came up with a second version where the steering angle was directly proportional to rudder pedal deflection. But this approach failed as well. At low taxi speeds, the pedal forces were unacceptably heavy, and at high speeds, heavy aerodynamic loads on the rudder made steering a real struggle. So they developed a third hybrid system. With this iteration, steering sensitivity only changed once the pedals were deflected past a certain point. But by the time it was ready, due to mounting pressure from Soviet leadership and increased scrutiny from state security services, orders came down to immediately transfer Prototype 155 to the Flight Research Institute for testing. This rushed transfer is likely what sparked rumors within the aviation community about test pilots deliberately driving the aircraft through mud and puddles. In reality, these were not wild stunts. They were routine evaluations of the unusual bicycle landing gear ground handling, carried out strictly according to the approved flight test program. At the Flight Research Institute, the engineering team recommended overhauling the nose gear steering so that light pressure on the rudder pedals would keep the wheels perfectly centered. The wheels were only supposed to turn with heavy pedal inputs. The German engineers flat out rejected this idea, feeling it would not let the pilot maintain directional control during the takeoff or landing roll. They decided to scrap that recommendation and keep refining their own third iteration. The reason testing dragged on for an entire year came down to the sheer complexity of the troubleshooting. The engineers were trying to dial in the perfect sensitivity for the nose-wheel steering, analyzing test pilot Ludwig Hoffmann feedback after every run. A lot of time also went into figuring out how to help the pilot intuitively center the pedals, as the controls had almost no natural resistance. The fix turned out to be highly effective and simple. They just rigged up some standard bungee cords to the pedals to provide artificial feel. The engineering team ran into a string of other challenges. Air getting trapped in the hydraulic lines required incorporating an automatic bleed valve. They had to redesign the centering locks on the outrigger landing gear, eventually allowing the wheels to caster freely within a 5-degree range before locking springs kicked in. They also installed a restrictor valve to keep the nose wheels from violently snapping when the steering system engaged. But despite the technical hiccups, the squat mechanism on the aft gear strut worked perfectly. During the takeoff roll, once the airspeed reached roughly 85 knots, the aft gear would smoothly retract. This happened so seamlessly that the pilot could barely feel it. The most efficient takeoff technique turned out to be holding slight nose-down elevator, which kept the takeoff roll to an absolute minimum before the aircraft lifted off at around 135 knots. Even though flight testing took longer than expected, the data gathered was incredibly valuable. Many of the theoretical and practical solutions first tested on aircraft 155 were successfully carried over to aircraft 150 and later found their way into East German designs. The concept of the aircraft squatting was even adapted for the Soviet M4 bomber prototype, demonstrating how the unconventional engineering of the era paved the way for future aviation advancements.